Okay, so let us go in with the study. So now we study the sequence an is equal to 1 plus 1 over n to the nth power. Okay, so this is this is the idea. So the first question is monotonicity. So from the example we made in the previous video, in the previous chapter, we had strongly evidence that the fact that an could be monotonically strictly increasing. So the first question is the following: is an monotonically strictly increasing? This is the first question. The second, is an bounded? So let us study point 1. So our hypothesis, okay, we want to prove that 1 plus 1 over n to the nth power is less or equal to 1 plus 1 over n plus 1 to the power n plus 1. Sorry, not less or equal, but strictly less. Now, notice that this problem is not so elementary, because here there is a basis which is larger than 1, here and here. Here we have n, the exponent is smaller, and this is good with the sign. But the problem is that here the basis with the index n is smaller than the basis with the index n plus 1. So it is very difficult. So there is a competition between the basis that decreases and the exponent that increases. This problem is not easy at all. It is not directly solvable with simple estimates and so on. So the problem is not elementary. So in order to solve it, we introduce the Newton's binomial. This is an important tool. Okay, and I introduce it in the form of a theorem that says, let A and B be real numbers n is natural number, then A plus B to the nth power is what? Is the sum of many terms. So I write sigma, now we are familiar with this symbol. So j from 0 to n, of this is a new symbol. You have a bracket, and then you have, it is not a fraction, just a number on up and a number down, nj, and here a to the n minus j, b to the j. Okay. Here we have nj, the strange parenthesis, which is called binomial coefficient. The definition of this binomial coefficient is that it is a fraction, and the numerator you have the factorial of n, which means the factorial of the number which is on up on the binomial coefficient. And here now you have the factorial of j, so the number that appears downwards. And then there is also the factorial n minus j. Okay, this is the definition. And you can find this binomial coefficient in various forms. For instance, by developing the factorial, here you have n times n minus 1, n minus 2, and n minus j plus 1, and then n minus j factorial. So it is clear this is the factorial, so you have the product of all natural numbers from n up to 1. So you just isolate, you gather out the numbers up to n minus j plus 1, then you end up with the factorial of n minus j. Okay, this is easy. And here it is a numerator. Let us go to the denominator. So you have j factorial times n minus j factorial, and of course you can simplify here, n minus j factorial here, n minus j factorial here. And so another expression that you find is the following: n minus 1 up to n minus j plus 1 divided by j factorial. This is a typical, an alternative writing that you find in many books, and also we will use here. So this is an alternative writing for the binomial coefficient n j. Moreover, write down n j binomial coefficient. Remember the definition, which is n factorial divided by j factorial, n minus j factorial is equal, here we put n factorial, and here n minus j factorial. This is a Baroque way of writing j factorial. And here n minus j factorial. Okay? And this is n minus j. So there is this equality which is important to nj is equal to n minus j. Okay. Other formulas that are important is what happens if there is 0 here, n 0. You have here n factorial, 0 factorial, and here n minus 0 factorial. Remember that by definition 0 factorial is equal to 1. Okay? And n minus 0 is n factorial. So whenever in the lower position in the binomial coefficient you have 0, The result here is 1. It is also important that here you have 1 in the second position, and again by definition you have n factorial divided by 1 factorial n minus 1 factorial. And 1 factorial is equal to 1. And to understand what is the final result of this, the final value of this binomial coefficient, remember that you can write n factorial by isolating n, and then writing n minus 1 factorial. And here you have again n minus 1 factorial. Then you cancel the two n minus 1 each other, and so you have n. So the message is that whenever you have 1 at the lower position of a binomial coefficient, the final result is exactly the number which is in the upper position in the binomial coefficient. And then you can also do some other computations. For instance, n2 is n factorial divided by 2 factorial, n minus 2 factorial. So you have n minus 1, n minus 2 factorial. Here you have that 2 factorial, of course, is 2 by 1, so this is equal to 2. And here you have 2n minus 2 factorial. So you have here n minus 2 factorial, n minus 2 factorial, and so you have n minus 1 divided by 2. And analogously, if you have n3, you have n minus 1, n minus 2 divided by 6. And what I want to stress is the following. Here you have fractions, and of course when you deal with fraction you can doubt whether the result of this fraction is a natural, is an integer number of none or not. So when dealing with this sort of binomial coefficient, it is always an integer number, because here, look, for instance, here you have 2 at the denominator, and here you have 2 consecutive natural numbers. And of course, when you have 2 consecutive natural numbers, one is even and the other is odd. Since one of them is even and then you just divide by 2, this must be natural. And the same appears here. Here you have 6. So you must have here a numerator, in order to have a natural number at the end, a number which is divisible by 2 and a number which is divisible by 3. But of course here you have 3 consecutive numbers. So at least one will be divisible by 2, and exactly one will be divisible by 3. So this is a natural number too. So the message is that nk with k between 0 and n is always a natural number. So I invite you to do simple computation in order to get acquainted with this Newton's binomial. And now I go back to the theorem, because the theorem says a very important thing. The important thing is that you can develop in a form which seems to be complicated, because here there is a sum and there is a binomial coefficient. However, it is just a sum. Here you have a power, which is much worse. So you can develop the power of a binomial into a sum of things, and this will be very convenient also here. And now, before proving this theorem, I will try to prove this theorem. There are many ways, but we will choose one. So before proving this theorem, I want to be sure that this is true for small n, okay? So examples of the simple examples of the validity of the Newton's binomial formula And the first example is very simple. With n equal to 0, a plus b to the 0 power, we know that this is equal to 1 because every number to the 0 power gives 1. And let us see what happens here. We have j from 0 to n, but n is equal to 0. And then you have here 0, j, a to the power, it was j or n minus j, and remember, r to the power n minus j, so 0 minus 0, which is 0, b to the power 0, and this is just 0, 0, a to the 0, b to the 0, this is 0 factorial divided by 2 times 0 factorial, a to the 0, b to the 0, everything here, every symbol, every number we wrote is equal to 0, so to 1, so this is 1. So it is a very complicated way of performing this computation, this power, but it is just to test the formula. So let us go to the power 1, a plus b to the power 1. This is equal to a plus b, of course. And this time we have to write down from j from 0 to 1 of n, which is 1, 1j, a to the n, so 1 minus j, b to the j, and this is like saying 1, 0, a to the 1, b to the 0, plus 1, 1, a to the 0, b to the 1. Okay, 1, 0 is equal to 1, a to the 1 is equal to a, this is equal to 1, and analogously here, so we end up with a plus b. So the formula works. Let us try for the second power 2, so for n equal to 2, we have a plus b to the second power. This is sum for j going from 0 to 2, and here you have a 2 minus j, b to the j's power, and here you have 2, 0, a to the second power, b to the 0 power, plus 2, 1, a to the first power, b to the first power, plus 2, 2, a to the 0 power, b to the second power. And so what you find at the end is a squared, because this coefficient is equal to 1, plus this coefficient is equal to 2, because there is 1 here. You know, when 1 is downwards, then you replicate the number which is upward. So a plus 2, ab, plus, and this is again 1, because if you want, you can do it in several ways, but we know that this is equal to 2, 0, because 2 minus 2, so this is equal to 1. And here plus b squared, which is exactly the formula of the square of the binomial here and here. So we are confident that it works, okay? And now we go for a sort of proof of this formula, okay? And so proof. So there are many ways of proving it. But as it happens when you deal with with theorems where natural numbers are involved, so the proof is to be made by induction. So rigorous proof can be made, must be made, should be made by induction. However, you can find this proof in books and so on. And remember what I told you when studying the induction. When you prove a formula by induction, you don't deduce, you don't find the formula. You already know for other reasons the formula, and then you use the induction just to prove it. But how can you know a priori the formula? Methods are so-called heuristic. You have to do some example and then extrapolate it, generalize it, and so on and so on. So what I want to show you now in the proof is not the induction, it's the heuristic. Okay? I find here more instructive. And then as a homework, I invite you to do the induction. The induction is not completely trivial. So at the end it is trivial, but doesn't go mechanically from the start up to the end. At some point you have to understand something. You have to do something. Okay? So we will do it by heuristic. So here we have a plus b to the n power. We want to prove it. A plus b to the n power. So let us reason, what does it mean a plus b to the n power? It means that you have to replicate the bracket a plus b n times up to n a plus b. You do it n times. Okay? Try to develop this huge product. And of course, you write this product as a sum of many polynomials. And what you do at each polynomial, what you have to do is to extract one term at every bracket. So traditionally, to do it in an ordered way, you just put in the first term, you choose the first term of every bracket, so you end up from the first parenthesis, from the first bracket you choose A, from the second you choose A, okay, it is A to the square, but I want to stress the fact that you are choosing one element from every bracket. From the third you choose A, and so on and so on, up to the nth. From the nth you choose A. Good. This is the first n. And of course this is made n times. And this is the first term. In the second term, you have to choose one element from each factor, from each bracket, and you do like before. From the first, you choose, for instance, A again. Sorry, I want it to be blue. And from the second, you choose A, from the third, A, up to the end when you choose B. So this is the color. Here again you choose A from the second and A from the third, and from the last one you choose B. So you perform a different choice in the second term from the previous one. In the first term you chose A from every bracket. For the second you choose A for the first n-1 brackets up to the last one where you choose B. There are two different choices. Let me write it. These are two different choices of contributions from every bracket. Okay? And you can think of the bracket like a box. There are boxes, and from every box you choose for every term in the development one single element. And you are not allowed to perform the same choice for all boxes 2 times. Okay? Every choice counts just one. So, of course, as you already understood, here there is a first contribution which gives you A to the n, and the second gives you the term A n-1 b. Oh, sorry. Of course, this last a to the n minus 1b can be obtained not only in this way, but with other choices. For instance, you can choose a from the first box, a from the second, a from the third, a from the last one, but from the second last, for instance, you choose b. And again, you end up with a minus n minus 1b. So notice that there are several different choices of contributions from the various boxes, from the various brackets, that amount at the end to a to the power n minus 1b. How much are they? Here, notice that you always choose a except once, except from one box you choose one time b. Of course, you have n possible boxes from which to choose b. So there are n different boxes from which to choose the unique b appearing here. So you will end up with a term which is n different boxes, a to the n minus 1 times b. Okay? This is a preliminary reasoning that we will generalize, but of course then you go with other choices. For instance, you put here two b's and so on and so on. And at the end, you have the last choice where you choose b for every box. And this will be b to the n. Okay? So, here what I just did is just developing this product and trying to understand from a higher point of view how I construct this development. Of course, you are used to do it mechanically, okay, without reasoning on that. But I want to understand the structure which is underlying the final sum, so I need to reason a bit. In particular, I need to isolate some principle. So let me introduce three remarks. The remarks say, first, every term in the development corresponds to a choice of one of A or B from every bracket. Second, every choice every choice appears only once in the whole sum. Of course, there are different choices that give you the same term, like here, two different choices that give you the term a to the power m minus 1b here, a to the power m minus 1b here. It depends from where we choose the b. Okay, every choice appears only one in the whole sum. And third, that says that due to the commutative property of the product and of the sum, different choices can result in the same contribution, the same term. of the type a to the power m minus j, b to the j. So let me give you an example in order to better understand this. If you consider n equal to 3, n equal to 3. So you see a plus b to the third power. I do the same passages I did before. This is a plus b, a plus b, a plus b. Okay, like before, from the first bracket a, second a, third a, plus b, plus a, plus a. Here all choices with just one b, and this is always a squared b. There are 3, so this is 3a squared b. Okay, and here plus ABB plus BAB plus BBA. And again, this is 3 AB squared. And then at the end, plus BBB. So of course, and you end up with A cubed with 3A squared B plus 3AB squared plus B cubed. From this example, probably you see very well what is the binomial coefficient. The binomial coefficient is just, here for instance, the number of possible choices that give you the same terms. This is just what I said in the previous general example. Okay? So, this is a nota bene. A binomial coefficient is nothing but and j is the number. Number is made with a sharp musical. I don't know why, but it's a sharp. In international language is the number. Number of possible choices that give a to the power n minus j, b to the j. Therefore, in order to know the binomial coefficient, we must count all possible ways of choosing the brackets, the j brackets, from where we pick b. The j b's. So here, for instance, look at this term here. We wanted to take 2 b's, and the possibility of taking 2 b's were from the second and the third, from the first and the third, and from the first and the second. 3 possibilities. Okay, and now we count in general. So, first, for the first box or brackets, we have n possible choices. N possible choices. So the first, the second, the first bracket, the second bracket, up to the nth. And we choose a b from there. So, for the second b, second factor b, we don't have n choices because for the first choice we already burnt one bracket. So we remain with n minus 1 possible choices. We have n minus 1 possible choices. We got all brackets that in principle are n, but except the one from which we chose the first one. At the previous set, the first factor b from the previous step. And now we know. So from the first we have n choices. For the second we have n minus 1. For the third, factor b, we have n minus 2. Oh, sorry. From the fourth, we have n minus 3 and so on. So from the j's, we have n minus j plus 1. Why plus 1? Count, just count. From the third, we don't have n minus 3, we have n minus 2. So in general, from the j's, we have n minus j plus 1. So the number of possible choices is n minus 1 up to n minus j plus 1. But this is not the binomial coefficient. There is a j factorial missing. Okay? So now the question is why there is a divisor j factorial missing. And this is why for every choice of the boxes now is counted many ways. For instance, look at here, this ABB factor could be obtained in two ways. And one way is choosing as first the second box and as second the third box. But you can choose as a first box where to extract B the third box and as second the second box. But this term appears only one. So when we counted it, we overestimated the possible choices. And the principle is that every choice of boxes, so in this way, let me write like that, in this way, every choice of boxes, is counted many ways, correspondingly to the possible ordering to all possible orderings of the j boxes, of the j brackets, from where to put all the b's, namely as the possible exchanges that are called permutations of j objects which is exactly j factorial. since we overcount it by a factor j factorial, so therefore the possible choices that give that the result in n a to the n minus j b to the j are from n, first choice, n minus 1 up to n minus j plus 1 divided j factorial, and this is exactly the binomial coefficient nj. Okay? This is the heuristic to obtain it. I stop this video, which is very long, and then I give you some comments.